You know that light has dual behavior, and in this topic of wave optics, we will be talking about the wave behavior of light. When we have the effect of multiple waves at the same point, at the same location, then it is the superposition principle that allows us to analyze the situation. Whether you talk of just simple harmonic motion, two or more than two, or something more complex based on simple harmonic motion like wave. It is about something happening at the same point. Look at these two waves. They both seem to be having similar type of behavior. When this is max, so is this. When this is zero, this is zero. So we say that they are in phase. If they reach a point at the same instant, then this will try to create maximum, this will try to create maximum, or this will try to create minimum, this will try to create minimum, negative direction. But they will complement each other. They won't act against each other. They would complement each other. Superposition principle just says that add the x values or y values. X equal to something could be the equation. Just add the two x's or two y's. So when they support each other, the result of adding two y's is something like this. When you mix two things, then they can support each other to the maximum extent. They can oppose each other to the maximum extent. And then there can be half-hearted support also, partial support. In fact, most cases are of partial support. Superposition principle tells you about all of these: extreme support, extreme opposition, then several possibilities of partial support or partial opposition, partial support or partial opposition. You can think of superposition as somewhat like vector addition also. If you have two vectors, they can support each other to the maximum extent if the situation is this: collinear arrows in same direction. That's the only way they can support each other to the maximum extent. So if this is 3 unit, this is 2, 3 plus 2 is 5. But 3 plus 2 is not always 5 in vectors, you know that. So there can be maximum opposition also. Look at this. Now here it is 3 minus 2 equal to 1. 3 minus 2 equal to 1. Maximum opposition, maximum support. But how about -15° angle, 30° angle, 90, 120? They are all partial support, partial opposition cases. So when you deal with y's or x's, which are positions, positions can be plus or minus. They are not distances, they are positions. When you deal with positions, it is somewhat like dealing with vectors. So superposition principle lets us analyze all these extreme opposition, extreme support, partial opposition, partial support cases. It's a general principle, not just 2, 3, 4, 5, 100, thousands. As long as all are at the same point. That is superposition principle. Superposition principle and interference phenomenon. They are not one and the same. Interference is a phenomenon. When you find 3 plus 2 is becoming 5, or then you say, okay, it's too loud or too bright. In case of sound, it will be too loud. In case of light, it could be too bright. So getting 3 plus 2, that process is superposition. The phenomenon is interference. Okay? So please try to see the difference between superposition word and interference word. Now, for example, if you look at them at whatever angle, 15, 30, then this procedure is coming from superposition principle. You won't call it interference now. Interference is the extreme. Extreme support or extreme opposition. So this is extreme support, and if it is extreme support, it is called constructive interference. So if you want constructive interference, then these things must be in phase. If there is slight difference in angle, except 0 degree, nothing is acceptable for constructive interference. Of course, 2 pi, 4 pi, they are just like 0. 2 pi, 4 pi, 6 pi, 8 pi. They're just like 0. Slight difference, it can't be called constructive interference really. But yes, you can analyze it from superposition principle. Extreme opposition. This wave wants the particle to, you can think from particle perspective, though in the case of waves, we don't need to talk about particles. These are non-mechanical waves. But when you learn waves, you learn it the string way, because string has got particles. It is easy to visualize particles. So if you just think of it as some string going up down type of thing, then think about this particle. This wave wants that particle to go up. This wave wants this particle to go down. Superposition principle says add the two y's, y1 plus y2, 1 minus 1 plus. That's maximum opposition possible. And if the two y's are equal, I mean here plus 1 minus 1 plus 1 minus 1, they're equal here. I mean amplitudes are equal. Then there will be 0, absolutely nothing. Flat string you will get. If you can get two types of waves like these in case of a string will not deform at all. They will cancel each other. So angle wise if we see, then they are 180 degrees out of phase. How do we know that? 180 out of phase? Because this is just like sine function, and at this point if you see, it is plus 1, here it is minus 1. It's just like saying this was at pi by 2 and this was at minus pi by 2. So the angle difference is pi. Alright, so in this case nothing, but that's not necessarily destructive interference always. For example, I could take it as maybe even then it would be called destructive interference, but now they won't cancel each other 100%. Yes, opposition is maximum. Opposition is maximum. But cancellation is not 100%. Because now it is 2 minus 1. This is, let's say, 2. So opposition is maximum. It is destructive interference. but 2 minus 1 is 1. So the result would be something like this. This fellow wins, but it has got half amplitude. This fellow wins, but it has got half amplitude. It becomes this. So something like this will come here. So one should not think that destructive interference means no sound, or destructive interference necessarily means no light. It could be so sometimes, but it doesn't have to be so all the time. Now, if you noticed, it was always a match. If you want always a match, you can't have different frequencies. How can you have a match always? Always support or always opposition. You want one below the other always. And for that you have to have same frequency. So if you have different frequencies, superposition principle will always work. So when I speak, my voice has so many frequencies mixed up. Superposition principle makes it sound like certain way. But we can't call it interference. Interference means there should be constant phase gap. One particle should be below the other, and that pattern should be followed continuously. To understand it even better, just think like this. Say initially there was enormous support, 1, 1, right? Fine. So here it would be 1 plus 1 equal to 2. But then see what happens. There is a support at this point. Below this, yes, fine, that's great. But below that, is there maximum support? No. So it doesn't work. So you have to have same frequency for interference to work. Superposition will always work. Same frequency or different frequency. So superposition principle gets you something like this. Yes, starting is with 2, fine. But then it's all sometimes partial support, sometimes opposition, it's all hodgepodge. All types of things are happening in this situation. Repeated pattern has to be there. For various points, either maximum support, maximum opposition. For various points, not just on one occasion or 2 occasions. So this thing happening for everybody, if you want, then you must have same angle difference. The sources must be coherent. Angle difference has got to be same. In case of sound, now think of it as synchronization, angle difference. When I say angle difference is 0, then you can think of it as absolutely perfect synchronization. Two musicians playing, and when this person hits note C, that person also hits note C. This fellow plays G, that fellow plays G, exactly at the same time. So it's just like synchronization when we say angle is 0. 0 means 0, 2 pi, 4 pi, 6 pi. And that's very easy to get in case of music. You take two speakers, drive them by the same amplifier or same CD player. So whatever plays on the CD, the same data goes here also, and at the very instant it goes here also. So when a note plays here, there also it plays, there also it plays. So they are in absolute synchronization, these two. And you get angle difference of 0. It's not that here if it is playing C, then C naught takes some time to reach there, and there's some angle difference created due to that. No. Yes, I can create some delay by some other means if I want. But in a situation like this, there would be no delay at all. Now, I can create delay. I can have this ear or this receiver placed at different distances. Sound has got speed, and to travel different distances, it would take different time. So yes, C naught might have left both speakers at the same instant, but because this is close, that C naught reaches early, and here C naught reaches late. So some angle difference can be created, but keep it fixed. When we say coherent, keep that angle difference fixed. Don't let this fellow move left, right, all that. Then interference won't work. Superposition will always work. Some mixture of all will be heard. But if you have fixed certain distances, then let that fellow be exactly there. So this is called path difference, L2 minus L1. So if you have fixed path difference, it will give rise to fixed angle difference or phase difference, fixed, constant phase difference, not variable phase difference. Variable phase difference will happen if this fellow keeps on moving here and there, or you keep changing position of some speaker. And then this player also should not be producing several frequencies. So it should not be like a typical movie song in which so many frequencies are mixed up. Pure note we want. Just C, it should play, or D note or F note, G note, A note, B note, minor, major, all that is fine. But as long as it is single, it is okay. But if you have a mixture, it's a problem. So monochromatic, chrome, single wavelength, monochromatic. Monochromatic word can be used. Now chrome somehow sounds like color, monochrome. But chromatic can be used for X-ray also. X-ray of just one frequency, monochromatic. So same frequency. If the path difference happens to be lambda by 2, you should be able to convert path difference to angle difference. A wavelength is just like saying one full revolution. A length of wave is just like saying one full revolution. So whether I say lambda or I say 2 pi, actually they are the same. In one case I am talking in terms of distance, in other case I am talking in terms of angle. So lambda distance is just like 2 pi angle. So lambda is similar to 2 pi. So lambda by 2 would be similar to 2 pi by 2 or pi. So when the path difference is lambda by 2, it is anti case, extreme opposition case. So if they have got same volumes, identical volumes, then nothing would be heard here. Nothing would be heard here. But if they have different volumes, then yes, cancellation would not be 100%, opposition would be 100%, but one is small, other is big, so cancellation won't be 100%. The problem with light is that how to do this type of thing. If you look at some incandescent bulb or some other vapor lamp, think of Bohr's model, all sorts of jumps electrons are making. And they are giving rise to so many lambdas. So many lambdas are going to be there. Yes, some may be dominant. And then how to synchronize? The jumps can be arbitrary. How to synchronize that? So jumps can be arbitrary. Synchronization is very difficult, but if we use the same lamp, somehow, imagine taking the same lamp and distributing its own light in two different paths. Then whatever happens, happens to both at the same time. So if you take the same source and split it into two different routes, even though some things are happening randomly, but it's happening to both of them. So that will take care of this problem. Getting a sound sound source which will produce one single note is very easy. Your computer can do it easily, playing just one particular frequency, sound frequency. But that's not so in case of light. So red color, well, there are so many shades of red. Blue color, we have problem everywhere when we deal with light. And moreover, even if you can get one frequency from one source, one particular shade of red color, then exactly that 100% closeness, that's very difficult. Because you're dealing with something like this. So the solution is that you take the same source and split light. Let it go through two different routes. So we can take two holes, Young's double hole experiment, or vertical slits, not just a pointed hole, but the whole slit, but very narrow. Young's double slit experiment. And then there are other ways also. The basic idea is same source, two different paths. Here is a very simple technique. Same source, light going straight. Same source, light going after reflection. So this light travels more distance than this light. So you have some path difference created. Path difference obviously will give rise to angle difference. Lambda is same as 2 pi. Alright, so we arrange for single source. We arrange for a source of monochromatic light, and then we let the light pass through two slits. This is the screen. Now in this drawing, how do you visualize the slit? Either you think of holes only, just holes, or imagine horizontal slits here, horizontal. So what does it mean? Imagine this cardboard coming towards you, and you cut it like this, make a slit. So you are looking at the cross section of the cardboard. Cardboard is coming towards your side and is penetrating the screen also. Its cross section is looking like this. And after you cut it, the cross section looks like this. So one way is this, other way is to just imagine that there's a hole here, there's a hole here. Whole visualization may be easy, I think. Two slits are separated by some distance. Screen is placed at some distance. If these distances are equal, which is what you find in this figure, then the rays here and here will be in phase. They will be in phase here and here. Because distances are same, if there is no path difference, how can there be angle difference? If this length is same as this length, there cannot be any angle difference. So they are in phase here and here. The story is after that. Look at different points on the screen, and you realize that for different points, distances may be different. That's the key. In reality, D may not look so big. In fact, this D will be very, very small, this D. But don't forget that we are dealing with light. You saw that frequency range. Sound is a different story. We can only hear from 20 Hz to 20 kilohertz, 20 kilo. And we saw that number for light. Here, little distance makes huge difference. For visible light, lambda is of the order of, say, 500 nanometer. 500 nanometer. So it's very little difference, very little distance difference that can make a lot of difference. D is small, and here also the path difference won't be huge. In this drawing it may look like so, but you don't need huge difference. You don't need huge difference for this phenomenon to be observed. By the way, what you actually find in this experiment, you find that there are regions of extreme brightness and extreme darkness, and there's a fall in brightness, gradual fall, not binary type of thing, 1-0 type of thing. Yes, these may look like binary, bright, dark, bright, dark. But binary means only 1 and 0. That's not the case here. So it's not just BD, BD. Between B and D also there is light between B and D. So brightness is maximum. It is minimum at D, 0 let's say. Then it falls gradually from B to D. So maybe you can think of it as somewhat like this. Well, just a moment. bright. That's where the peak should be there. So it's a gradual fall in brightness. It's a gradual fall in brightness. It becomes 0, but then again rises. It again rises. Again becomes 0. This pattern goes on and on and on. So there are several points at which there is pitch darkness, these, and there are several points where there is extreme brightness. So why do you find these things? Because if I talk about B, brightness, these distances were same, right? So whatever has happened in path has happened later on. At the center you find B because at center there is no path difference. Total lengths are same. But then here you find there is difference. If there is lambda by 2 difference, it is like saying pi difference. It's a gone case, dark case. But again, here brightness, and it goes on and on and on. At the center, there is going to be no path difference. So at the center, it is going to be constructive interference. At the center, the rays start in phase, travel the same distance, so they arrive in phase. Constructive interference. This question is for this particular point only. Now, if we modify the experiment, now we find that there is phase difference of lambda, there is path difference of lambda by 2. Path difference of lambda by 2 shifts the phase by pi. How do you modify the experiment? There are techniques. By inserting some material in the path, one of the paths, inserting some material in one of the paths. So you can possibly insert something here, and that thing, because of its refractive index, creates some optical break. So that shifts the phase by pi. So if you have pi phase angle at that location, now there is going to be destructive interference. So here this thing is inserted right here. It could be inserted later also. So here this fellow is creating lambda by 2 shift. So several B's that I had marked in the center, at the center, the path difference will be 0. The next B path difference will be lambda. The next B, it will be 2 lambda. Next B, 3 lambda. As long as you are having some integral multiple of lambda, it's just like saying multiple of 2 pi, integral multiple of 2 pi. Saying integral multiple of lambda is same as saying integral multiple of 2 pi. And you know, when two sine functions are different by 2 pi, they are actually not different. So one fellow helps the other fellow extremely, and you find constructive interference. Now it could be minus side also, plus or minus doesn't matter. So bottom side also, here also, here also. And between 0 and lambda comes lambda by 2. Between lambda and 2 lambda, 3 lambda by 2. So that means between one B and the other B, between 0 and lambda, there has to be a D, lambda by 2. And gap between two B's, subtract these two, subtract these two. Gap between two B's is same as gap between two D's. Now that looks more realistic. D is really small, this D is really small in comparison to that D. So when we say little, when we say the path difference is there, it's very little path difference. So don't expect B and D, bright and dark regions, will be distance apart. They will be very, very close. They will be very, very close. And in this figure, bottom ray would travel more. But if I take a point here, Same can be said for the top ray. So it all depends which point are you talking about. Here, bottom ray travels little more. So that little extra distance is giving rise to path distance. And you saw in what range we talked of path difference? Path difference being lambda, 2 lambda, 3 lambda, or lambda by 2, 3 lambda by 2, 5 lambda by 2. What is the range of lambda? Let's say nanometer, say 500 nanometers. 500 nanometers path difference range. How little it is. The difference in distance traveled by these two rays, if I say that is of the order of 500 nanometers. And when I say 500 nanometer, I am talking of visible region. You know how ultraviolet, anyway, for ultraviolet you can't see bright and dark. That does not mean that in ultraviolet you can't get interference. You won't be able to see it, that's it. No assignment for today. We stop now.